welcome to the new lecture. Today we are going to learn about arrangement of resistors in circuits. So we know that there are two type of combinations of resistance are available. First one is series combination and second one is parallel combination. So in series combination, in electrical circuit, the components are arranged in a line, that is called a series combination. So here in this figure, the current I is flowing from the battery having voltage V, and I is passing through resistor R1, R2 and R3, which are connected in series. So there is a potential drop across R1, that is V1, and potential drop of V2 across R2, and potential drop of V3 across R3. So by Ohm's law we have V is equal to IR. So in series combination the voltage is varying across the respective resistors. So we can write the effective voltage as V1 plus V2 plus V3. So that is written over here, and by Ohm's law we know that V is equal to IR. So the effective voltage drop or effective voltage can be represented as IRS. There is no change in the current. In series combination, current is same across each resistance. So current will be the same throughout the circuit. So RS is the effective resistance of in series combination. So IRS is equal to IR1 plus IR2 plus IR3. So V1 is the potential drop across R1. We have already know from this class. So here the current is the same in the circuit. So we can rewrite this equation as effective resistance in series combination, that is RS is equal to R1 plus R2 plus R3. And if we increase the number of resistance or number of resistors R1, R2, R3, etc. to Rn, then the effective resistance in series combination will be very high, but the current will be the same. That is called in series combination. So if we increase the resistances or resistors R1, R2, R3, the effective resistance will be very high. So now we will come back to parallel combination. So in parallel combination, the components are arranged parallel with each other. So here the components are resistors R1, R2 and R3, which are parallel to each other, and a current I is flowing from the battery, and when it reaches this point the current is divided into three branches. I1 current is passing through R1, and I2 current is passing through R2, and I3 current is passing through R3. So in parallel combination we have to note this point: potential drop across each resistance is same. So what will be the potential difference across R1? That will be V. What will be the potential difference across R2? That is also the same, capital V. And what will be the potential difference across R3? And that is also V. So the potential drop across each resistance is same in parallel combination. So the effective current, the total current I, can be written as the combination of I1, I2, I3. Because I have raised here and split it into three parts, and again from this point all the three currents meet together and rejoins to the source. So I is a linear combination of all the three currents. So we know that V is equal to IR from the Ohm's law, so we can rearrange the equation in terms of V and RP. So Here Rp is the parallel effective resistance in parallel combination. So we can write V by Rp is equal to V by R1 for I1 current, and for I2 current it will be V by R2, and for I3 V by R3. So here the potential drop is the same. So we can remove this V and rewrite this equation as 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So the effective resistance can be calculated in parallel combination, that is Rp. So similarly, when we look in the series combination, if we increase the resistors R1, R2, R3, etc. to Rn, the effective resistance in parallel combination will be very less. That is, if we increase the R1, R2, R3, the effective resistance in parallel combination is going to be decreasing. So here we look at an example. So in parallel combination, if we are considering a battery of 12 volt and we have two resistors R1 12 ohm and R2 of resistance 4 ohm, in the parallel combination we have the effective resistance equation as 1 by R is equal to 1 by R1 plus 1 by R2. R is the effective resistance. So if we rearrange the equation, we will get R is equal to R1 into R2 divided by R1 plus R2. And if we put the values of R1 and R2 in this equation, we will be getting 3 ohm as the effective resistance in parallel combination. So the final current flowing through the parallel combination can be calculated as I equal to V by R. We can substitute the value of V, that is 12 volt, and R from this 3 ohm. So I is 4 ampere. So 4 ampere current is passing through the resistors R1 and R2 if a battery of voltage 12 volt is connected in parallel combination. So similarly, in series combination, if we have a battery of 6 volt and if we have two resistors R1 and R2 of 4 ohm and 2 ohm respectively, then the series combination, the effective resistance is going to be R1 plus R2. So if we substitute the values of R1 and R2, we are getting 6 ohm. So in order to calculate the current, we are having the Ohm's law. By rearranging the equation of Ohm's law, I is equal to V by R, and substituting the values of V and R, we are getting 1 ampere current in series combination. Okay, so moving on, here there is a figure. We have two bulbs which are connected in series with a battery and having a switch, and here two bulbs are in parallel combination. So here, if one component in the series combination is breaks down, which means the whole circuit will burn out in series combination. But in the parallel combination, if one component breaks down, the other components will function. Each component has its own path. That is, each has its own independent circuit. Here there is only one circuit, so if one bulb has fused or burns down, the circuit is collapsed. So in a parallel circuit, if one bulb is not working, then the other bulb surely works. So moving on, so in series combination, we have studied that the same amount of current flows through all the components. That is, I current is flowing through the resistors or bulb if you are considering. Second point, in an electrical circuit, components are arranged in a line. Then, when resistors are put in a circuit, the voltage across each resistor is different, even though the current flow is the same through all of them. And if one component breaks down, the whole circuit will burn out that we have studied here in series combination. And in parallel, the current flowing through each components combine to form the current flow through the source. That is, we have found out from here. The current flowing through each resistors combine to form the current flow through the source. In an electrical circuit, the components are arranged parallel with each other. When resistors are put in this circuit, the voltage across each of the resistors is the same and even the polarities are the same. So in the parallel circuit, other components will function even if one component breaks down. Each has its own independent path that we have learned earlier. If this bulb is not working, then this bulb will work since the current will flow in this circuit. So this is the conclusion of this lecture, that is, in series combination or in connection, the current will be the same across all the resistors, and in parallel the currents will split up. And with respect to voltage, in series combination the voltage will add up to the circuit voltage, but in parallel same voltage across all parallel branches. And in series, resistance is adding resistance increases to total R, total effective resistance, that is capital R. In parallel, adding resistance reduces total effective resistance. So in series combination, we have an example string of Christmas lights. They are connecting in series combination, and power outlets in house which are connected in parallel combination. So I hope this lecture is clear to everyone. We will come back with a new lecture. Thank you.